This is Andreas Reinhardt from the Technical University of Clausthal, Germany, and I'm presenting our work on the length of the sequences used in sequence-to-sequence and sequence-to-point learning for non-intrusive load monitoring. We see a growing number of NILM methods that employ neural networks, and in particular the sequence-to-sequence and sequence-to-point methods have been shown to achieve very good disaggregation results. And for that reason, we've tried to investigate in more depth to see if there was even more to gain by parameterizing them correctly. To be shown here on the left, we see the sequence-to-sequence method, which makes a prediction of an appliance's power consumption for the same duration as the input sequence. On the right-hand side, we see the sequence-to-point method, which takes a sequence at the input, but then only makes a prediction for a single point at the center of that input window. Both of them, however, have one parameter that needs to be defined, and that is the length of the input sequence. The longer the sequence, the more historic past data is available to the method. At the same time, training takes much longer because there's more data to process. When we're looking at different data sets for non-intrusive load monitoring that have been published and released online, we see one further aspect, and that is that these data sets differ in the sampling rates at which they have been recorded. So of course, if we have a fixed length of the sequence, that data set sampling rate has an impact on the extent of historic data available. And similarly, NILM-TK, as a toolkit for non-intrusive load monitoring, has a feature to reduce the tamper resolution further by applying a downsampling approach and just aggregating a number of data points into a single one. So for that reason, we propose a new notion of the effective sequence length, which is the product of the sequence length of the NILM method, like sequence-to-sequence or sequence-to-point, multiplied by the sampling interval of the data, multiplied by a data reduction factor that is being applied in NILM-TK. That would just default to 1 in case no downsampling is applied. So theoretically speaking, the choice of the sequence length would influence the appliance recognition or appliance disaggregation accuracy, right? That's exactly what we thought. So we said, let's look into this more methodologically. And the first step, what we've done, was to check what does related work do when it comes to picking the right sequence length. And it turns out that the default sequence length in NILM-TK is 99 samples. In another paper though, we've seen that the authors have experimented with sequence lengths of 50, 100 and 200 samples, but the data set sampling interval was 6 seconds. So essentially those sequence lengths look back into 6 times these figures of seconds into history. In another publication, we see a sequence length of 599, but actually use that in conjunction with 2 different data set sampling intervals, one at 1 Hertz, one at 1/6 of a Hertz. So that effectively maps into an ESL of 599 or 3,594 seconds. So that's 10 or even 60 minutes. And then again, Jack Kelly, when using sequence-to-sequence, said that the sequence length choices were governed by the appliance duration. So we assumed that to mean that it's the length of the activities of these appliances. So what we've done was to run an experimental study. And we wanted to look into how does the sequence length impact the F1 score and the NDE of the disaggregation. So we used 4 weeks of input data from the DREAD dataset, for which the sampling interval is 1 second. We considered 4 appliances, the fridge, cooker, microwave and washing machine, and then picked different ESLs from 90 seconds to 6 hours. For the sequence-to-sequence method, that's what the results look like. So on the left-hand side, we see the F1 score results, and on the right-hand side, we see the NDE scores. And what we can take home from this diagram is that both of them pretty much clearly show that there's a lot of oscillation and it doesn't look like there's an optimum value. Looking at the same results for the sequence-to-point methods, the trends that we observe are still somewhat similar. So what we've done was just to use a Bezier interpolation of the data points we've collected in order to see what the general trend of these curves is. For large values of the effective sequence length exceeding 3 hours or 10,800 seconds, both the F1 score is deteriorating and also the NDE as an error metric is going up, showing that we're getting more and more of an error. For the sequence-to-point method, it's not quite as pronounced, but it becomes a bit more clear here that we see different optimal points where the F1 score is peaking to the positive or the NDE has a minimum value, which would indicate that those could be candidates for the perfect choice of an ESL. And this is just summarized in the table. So for each of these appliances, we've looked at what is their active duration on average, because that's what Jack Kelly used when picking the sequence length. And we also looked at what's the ESL choices for which we could get the maximum F1 or the minimum NDE. We see the diagrams coming up here. So we slightly extended our testing and training data time frame. We increased the number of epochs for the neural network just to make sure that we don't see insufficient training. And also we raised the barrier from which we used a reduction factor of 10 to ESLs in excess of 250 seconds. And then we compared that to the values from related work, specifically 99, 599, as well as the average activity duration. And in all these bar graphs, we see on top an arithmetic mean of the scores that we see in the bottom. So we see sequence to sequence on the left, sequence to point on the right. And what we can observe is that a value of 99, the standard in NILM-TK, isn't faring so bad, particularly when compared to 599, where we can see that it has actually scored the worst results across those 5 experiments we've run. Looking into the average appliance's operational duration, that is kind of hard to tell. It's slightly better in the sequence to sequence, slightly worse in sequence to point. Not a bad option at all though, but naturally, as expected, the ESL values for which we've scored the highest F1s or the best NDEs also excel in their particular categories. Sometimes you may say this takes a long time to study each appliance individually and run such an analysis to find out what the best ESL choice for that particular device is. So in a last step, we've added one more result, and that is we've added all the 4 F1 scores and NDE scores together, such that the scale is no longer from 0 to 1, but 0 to 4, because we have 4 appliances in the data set. We see this diagram in the diagram on the left. And our intention was then to again apply that interpolation step and try to work out, is there a particular value for which we can observe a global optimum, which would be a compromise for all the appliances. And in fact, only one of those curves shows such a value in the considered range of values, and that's the F1 score of the sequence-to-sequence algorithm, which peaks at an ESL of 5,614 seconds. So we've repeated that evaluation and added to the bar graph from the previous slide one more set of bars to the very right, which is 5,614. And interestingly, it still has a very good performance, much better than the default setting of NILM-TK, not as close as when we be setting device individual ESL levels, but still it is kind of fairly close to that best situation we can see. And at the same time, we also observe a fairly balanced outcome. And so to summarize, what we've shown here is that sequence to sequence and sequence to point are fairly well-performing NILM methods, but the main parameter they need for configuration, the sequence length, has seen very little consideration. In particular, we see people modifying that sequence length, but not understanding that it also depends on the data set sampling interval and the reduction factor of NILM-TK to see what that actually maps to in terms of the actual time extent in hours and minutes of historic data available to the algorithms. Ideally, one would pick a different ESL choice for each appliance under consideration, because that gives you the best disaggregation result at lowest errors. But still, we showed we can actually work out a compromise value that is still close enough to the maximum, but then would only use the same value across all appliances. So our take-home message at this point really is to choose that effective sequence length value carefully, and I wouldn't recommend you to stick to the default value if you're after the best performance for sequence to sequence and sequence to point. Thank you for your attention.